Hello everyone. Laws of let's define forces. Forces are the causes for any change in velocity and acceleration. It's a vector quantity. Therefore, the net force, let's define here the net force is the vector sum of all the forces acting on an object. This net force, sometimes called total force, sometimes called resultant force, or unbalanced forces. The net force is equal to zero when the acceleration is actually equal to zero, which means the velocity is constant. For instance, if we have an object, a stationary object like this one here, find this one here, the net force on this object equal to zero because the acceleration in this one is zero and the velocity of this object here is equal to zero. But if this object is actually moving with velocity, with constant velocity, this means that the acceleration here it's equal to zero and the net force is equal to zero. Now let's define the classes of forces. There is a contact force which involves with the physical contact between two objects, like this object here. Just change the color here. This object here acting on this object here. So this is M1, for instance, and this is M2. There's a contact between them. In this case, it's called contact force. So the other type of class of forces is the field force. Field force, example, if we have here two magnets, here, this is the north, and this is the south here. There is a force between the north and south in this case here, just here. So there's a force between these two magnet poles. This type of force is called field force. This one here, field force, which means there's no physical contact between these two objects. In physics, we have different types of forces like gravitational force, electromagnetic forces, nuclear forces, and weak forces like van der Waals force. Now let's define Newton's first law. Newton's first law. In simple words, a stationary object will remain stationary and a moving object will remain moving unless there is an external agent act on this object, change its status. Let's have a look to this model. In this model, as you can see here, there's an astronaut. Here, there's an astronaut and there's a shuttle in a deep space. No gravitational force on this model at all. As we can see here, the astronaut and the shuttle will remain at rest unless there is a thrust force acting on the shuttle, for instance, and make it move. Once a thrust force acting on the shuttle here, the status of the shuttle here is changed from stationary into a moving because of the thrust force, this one here. Again, a moving object will continue in motion with constant velocity and a stationary object will remain stationary. Let's define a mass. A mass is a property of an object that specifies how much resistance an object exhibits to any changes in its velocity. Mass is measured in kilogram in SI units. Mass is an inherent property of an object. It's independent of the object surrounding It's also independent of the method used to measure it, and most importantly, it's scalar quantity. Usually, people get confused between mass and weight. Mass is a different quantity than weight. Weight is equal to the magnitude of the gravitational force exerted on an object. So it's vary with location. Now let's identify Newton's second law. Before going further with the Newton's second law, let's have this simple model. In this model, two shuttles, as we can see here, shuttle A and shuttle B. Shuttle A with 400 kilogram and shuttle B with 100 kilogram. If we apply the same thrust force on both shuttles, and this thrust force equal to 500 Newton. So what will happen here? Which one will reach the end point first? So if we start this experiment here, let's see here. As we can see here, shuttle B will reach the end point first because it has a larger acceleration compared to the acceleration of shuttle A. From the previous model, we noticed that larger mass will have smaller acceleration and smaller mass will have larger acceleration. In other words, the acceleration is inversely proportional with the mass. This can be summarized in Newton's second law. The net force acting on any object equal to ma. Sum of all forces equal to ma. Since the force is a vector quantity, so we will have here sum of all forces on x equal to max, and sum of all forces on y equal to may, and sum of all forces on z equal to az. Let's have this simple example here. If we have an object with mass m, two forces F1 acting on this object to the right and F2 acting on this object to the left. F1 here, the magnitude for F1 equal to 6 Newton, and the magnitude for F2 equal to 2 newtons. If the mass of the object here equal to 2 kilograms, find the acceleration for this object. So sum of all forces, or the net force, in this case there is no y or z coordinates, just x-axis. Sum of all forces on x here equal to no need to say ax because no other acceleration we have here. In this case here, the net force here, in this one here, just see, the net force here equal to ma. In other words, 6 minus 2 equal to 2a, or we can say that acceleration equal to 2 meter per second square. Remember, this is 6 to the right and this is 2 to the left. Now let's identify Newton's third law. Newton's third law can be summarized as the following. Wherever you have an action, there is a reaction, same in magnitude, different in direction, which means forces always occur in pairs, or there is no single isolated force in nature. Since we have two forces, one of them is action and the other one is reaction, it doesn't matter actually which one is the action and which one is the reaction. Let's have a simple example here. We have two masses, m1 here in contact with m2. And as a matter of fact, here we have two forces, F2 on 1 and F1 on 2. So F1 on 2, in this case, it's directed this way here. Let's change the color here. This way here, it's F1 on 2. And we have same force, same magnitude, but different direction. This one is F2 on 1. So F1, 2 magnitude equal to F2 on 1. And F1 on 2 as a vector equal to minus F2 on 1 as a vector. One very important force we have to discuss here is the normal force. So let's define here the normal force. A normal force exists if there is a direct contact with a surface. Let's consider the following cases. So if we have here a wall, let's see, wall, and then there is an object in contact with this wall here. So this is the mass M. The normal force is directed in this case to this one here, and it's simple as capital N. And if we have a surface like this here and an object with mass M, the normal force is directed this way here. And if we have an inclined surface like this one here with mass M, the normal force, it's normal to the surface like in this one here. And if we have an object and in contact with a ceiling, in this case here M, in this case the normal force is directed this way. Now let's have an example. An object has a mass of 2 kilograms. The object remains at rest, which means it's not moving at all. There's no acceleration on this object on the floor. Find the magnitude of the normal force exerted on the object by the floor. So let's just have a simple sketch for this case here. So we have an object here, an object on the floor in contact with the floor with mass M here. Now let's ask this simple question: how many forces act on this object? As we can see here, we have two forces. One of them is the weight, and it's directed downward like in this one here, and it's mg in this case. And the other one, since we have a direct contact with the surface, there is a normal force, and this normal force is directed normal to the surface in this case here. So let's apply Newton's second law. Now, summation of all forces, in this case just y we have here on y equal to m-a-y. Actually, there's no need to say ay in this case here, since the object remains at rest, so it means the velocity is constant in this case, and there is no acceleration on the object. So this one here, it's equal to 0. So normal, this is the normal here, normal minus mg equal to 0, which means normal equal to mg. By substituting here 2 multiplied by 10, it's 9.8, but now in this case just we can take it 10, so it's equal to, in this case, 20 Newton. Now let's have this model. As we can see here in this model, we have two tractors connected with this rod in between them. Now on the left tractor here, there's a driving force, it's minus 10. This one here is the driving force, this one here minus 10. In the right tractor, the driving force is 10 Newton. In this case, the system will remain stationary, no moving whatsoever. But when we modify the left driving force to minus 5 here, let's see what will happen. The net force is going to the right in this case here. But when we modify the net force into minus 20, the net force will be acting to the left. Example, In the figure, if the object is in equilibrium and F1 is equal to 10 newtons, theta equal to 30 degree, and m equal to 4 kilograms, how much the normal force exerted on this object? Now, in equilibrium, it means the net force equal to 0. The acceleration actually is equal to 0, so sum of all forces, it's equal to 0. So to start or to calculate the normal force in this case here, let's analyze F1 here. So F1 actually it's equal to, or let's just have free body diagram in another way. So this one here, this is m, and this is the weight here, mg, and this is F2, and F1 here in this case, it has an x component which equal to F1 cosine theta, and a y component F1 sine theta, and we have also a normal force in this direction here. Now what we need here is to calculate the normal force, this one here, this guy here, we need to calculate this normal force here. Now sum of all forces on y, in this case here, sum of all forces on y, this y here, equal to 0. So sum of all forces here on y equal to 0, which means normal plus F1 sine theta equal to mg. And in this case, normal equal to mg minus F1 sine theta. M is equal to 4 and g is equal to almost 10. F1 here it's equal to 10 and theta is 30, sine 30, it's equal to 0.5. So 4 multiplied by 10 minus 10 multiplied by half. Force, or the normal force in this case here, equal to 35 Newton. Example. We have an inclined surface like this one here. So this is theta here, and this is the mass m. Question. Show all forces acting on the block. So what is the forces acting on the block? So let's identify all the forces acting on this block, assuming that there is no friction whatsoever in the inclined surface. So in this case, we have mg, it's directed down or perpendicular to the earth, and there is a normal force is normal to the surface, is this one here. So this is mg and this is n. Now to solve this, we have to rotate the coordinate in such a way, make the y-axis matches with the normal force, and this is the x in this case here. So this is y and this is x. So the new graph will be something like this. So the same here, same this here, and this is theta here. So this is the normal force, and this is actually the y-axis, and this is the x-axis. The weight is directed this way here. Now let's summarize the graph here. So this is the inclined surface, this one here. This is the object with mass m. The forces acting on this one here is the weight, which is directed this way here, mg, and the normal force after rotating the coordinates matches with the y-axis. So this is the normal force, and this is actually the y axis, and this here is the x-axis. X-axis. Now, if this is theta, so this will be, and this is 90 degree, this will be 90 minus theta, and this is will be theta. So this angle here is actually theta. So when we analyze the weight here, it will have a y component, which is mg cosine theta, and mg, this one here, mg sine theta. So the force, the driving force acting on this in this object and make it slides down the hill here, it's equal to mg sine theta. In this case, sum of all forces on y equal to, since the velocity of the object on y equal to 0, there is no acceleration in this one here, so it's equal to 0, or normal minus mg cosine theta equal to 0, so the normal force equal to mg cosine theta. Now to find the acceleration, now sum of all forces on x, this is the x-axis as we mentioned before, this is the x-axis here, this one the x-axis here. After we rotated the xy coordinates, sum of all forces on x equal to max, which means the only force on x in this case here is this one here. So mg sine theta, the only driving force on x, it's equal to mg sine theta equal to max, or in other words, ax actually it's equal to g sine theta. Let's double check this one here. If theta equal to 0, which means the object on the flat surface, there is no acceleration on x, which makes sense for this one here. And if theta equal to 90 degree, in this case ax it's equal to g, which means the object will fall freely. Let's have another example. Two objects in contact with each other on a frictionless horizontal surface. A constant horizontal force F is applied to M1. If the two objects remain in contact, what is the magnitude of the contact force between the two objects in terms of F and M2? Let's have here a quick sketch for the question. So we have here a flat surface, and we have here two objects, name them M1 here, and this one it's M2. Now the acting force on M1 here is F, this one here. So let's define the forces in this whole system. Let's agree that we have here two systems, M1 and M2. Now M1, there is a normal force, there's a weight directed this way here, mg, m1g, and there is a normal force, this one here. And M2, there is an mg, which is directed downward here, m2g, and there is a normal force directed this way here. Now, don't forget that there is a contact between them. So, and as Newton's third law states that wherever you have an action, there is a reaction. So forces comes in pairs, which means M1 acting on M2 by F1 on 2. So we have here force F1 on 2, and 2 is acting on M1 with the same F1 and 2 but in different direction, and let's do it in this way here, F2 on 1. Let's make the figure bigger to clarify things. This one here, so we have here M1 and we have here M2. So we have F here, and we have F2 on 1, and we have here F1 on 2. We have the weight M2G, and we have the normal. It has to be the same length, by the way, and this one here, the M1G, and this is the normal force. Now let's start solving this. Sum of all forces, let's take the system number 1, system number 1 here. Sum of all forces on X equal to M1A. So M1A, let's name it X. Now on X here we have F and F1, F2 on 1. So F minus F2 on 1 equal to M1AX. So this is the first equation here. Now on the second system here, we have sum of all forces acting on M2 equal to M2A, or Fx equal to M2A, or F12 equal to M2A. And this is the second equation here. If we add both equations, and remember F12 it's equal to F21, same magnitude, different in directions. This means F here, if we add this equation here, this one here with this equation here, you will get F equal to M1 plus M2 multiplied by A, or in other words, A equal to F-AX actually, divided by M1 plus M2. Since F12 equal to M2A, and we just calculated here AX here, so F12 equal to M2F divided by M1 plus M2, and this equal to the magnitude for this one here, equal to the magnitude of 2 on 1. Another important example we have to consider here is the Atwood machine. So in this Atwood machine example here, we have a pulley, frictionless pulley, in this one here, and two objects, let's name them M1 and M2, connected by unstretchable flexible rope. Question: find the tension of the string in the Atwood machine, assuming that the rope is massless. If we assume that the system is moving this way here, so the acceleration is going this way here, and as we can see here, we have two systems, system 1, this one here, and system 2. On system 2, there's two forces acting on M1. The forces are the weight, which is directed downward, M1G, and the tension actually is this one here, is the tension. And on M2, there's again the weight is directed M2G, and the tension directed this way. And since the rope is unstretchable, made from the same material and flexible, the tension will be the same on both cases here. And the acceleration for the system is going up here, and it's going down this way here. Now, starting from system 1, we have here M1G and we have here tension. In this case here, tension minus M1G equal to M1A. Now, this is the first equation here. Now, for the second case here, it's tension minus M2G equal to, the acceleration is going down, it's minus M2A, or the force with the acceleration start with it. In this case here, M2G minus tension equal to M2A. You can consider this or consider this. This one comes from forces up positive, forces down is negative, acceleration up is positive, acceleration down is negative. Or this one here, take this trick, the force with the acceleration start with it, and that's it. And by the way, this is the same as this one here. So this is the same as this one here. So this is equation number 2. Now, adding these two equations together, this one here, and this one here, you will get this M2G minus M1G equal to M1 plus M2A. In other words, the acceleration actually it's equal to M2G minus M1G divided by M1 plus M2. Once we calculated the acceleration, we can easily calculate by applying this acceleration in one of these two equations, either this or this. So when we substitute this acceleration on this equation, the first one here, you will get tension equal to M1 and A. We just calculated this one here. It's M2G minus M1G divided by M1 plus M2. This is the acceleration plus M1G. And this is the tension on the rope. Let's simplify the tension here. Tension equal to M1 M2G divided by M1 plus M2. Example. In the figure, M1 is equal to M2, which is equal to 2 kilograms, and theta equal to 37 degrees. Find the tension in the rope, assuming that there is no friction in the pulley, not even on the inclined surface. Ignore the rope mass. This example here combining two different cases at the same time. So we have inclined surface and we have outward machine we just mentioned before. To work with this example, let's just summarize the situation. We have here, this color here, we have here two different systems. This is system 1 here and this is system 2 here. Now let's start on system 1. How many forces we have here on system 1? On this case here, we have the weight, which is directed this way here, mg, and we have tension. In this case, it's T. We have here normal force, in this case here, and there's no friction again. And on system 2, we have here the weight, which directed M2G, directed downward, and we have here a tension in this case. And remember, since the same rope, same material, flexible and stretchable rope, it will be the same tension between the two systems. Now, starting from this easiest one, which is system number 2. So at system number 2 here, we have the one with the acceleration start with it, which means M2G minus tension equal to M2A. Now on system 1, on this one here, we have the weight, now we need to analyze the weight, because in this case here we have to rotate the coordinate. This is x and this is y. So again, we just find that this is theta here. So we have mg cosine theta, and this here it's equal to mg sine theta. Okay, sum of all forces on x, this is x here, sum of all forces on x, it's equal to ma. Now the force with the acceleration start with it, which means tension minus mg sine theta equal to m1a. Now we set up all the equations here. Now this equation number 1 and this equation number 2. You add both equations together here, you will end up with m2g minus, this is m1g sine theta equal to m1 plus m2. In this case, acceleration equal to m2g minus m1g sine theta divided by m1 plus m2. Substituting this acceleration back on equation 1 or 2, let's find the tension. So m2g minus tension equal to m2a, or tension in this case it's equal to m2g minus m2, and the acceleration we just calculate this one here, this acceleration here, m2g minus m1g sine theta divided by m1 plus m2. Just substituting the numbers, you will get tension in this case equal to 16 Newton. Another example. Two objects on horizontal frictionless surface connected by a rope. F1 or F just applied on M1, as we can see here. Find the tension given that F equal to 10 newtons, M1 equal to 3 kilograms, M2 equal to 1 kilogram. Ignore the rope mass. Now to solve this, let's have a look to this diagram here. We have M1 here and we have M2, and F is applied on M1. Now there's a tension directed on M1 this way here, and a tension on M2 directed this way here. And don't forget that we have here the weight and normal force, and the weight for this one here, and normal force on this one here. Now to solve this one here and to find the tension on the rope here, let's have this one here. Sum of all forces on X equal to M1A. Now on system 1, this one here, on system 1 here, we have F minus tension equal to M1A. So F minus tension equal to M1A. And this is the first equation we have here. Now on system 2, this one here, on system 2, now tension actually it's equal to M2A, and this is equation number 2, this one here. If we add both equations together, we will have F equal to M1 plus M2 times A. In other words, acceleration equal to F divided by M1 plus M2, or acceleration equal to 10 divided by 4. 4 because we have 3 kilograms and 1 kilogram, and this is the acceleration. Now tension equal to M1 or M2A, or tension equal to 1 in this case here, multiplied by 10 over 4, or tension equal to 2.5 newtons. Example: a 30-kilogram object stands inside an elevator. Calculate the normal force acting by the elevator if the elevator is moving up and the elevator is moving down. So let's consider the first case. The elevator is going up. This is the first one here. So we have an elevator here, and we have an object on this inside the elevator. Now, the forces acting on this object is the weight, its mg, and the normal force exerted by the elevator on the object. This is the normal force. Since the elevator is going up in this case here, so the acceleration is going up in this case here, sum of all forces on y equal to m a y, or the force with the acceleration start with it, which means normal minus mg equal to ma. So the normal force equal to mg plus ma, or you can say that normal force is greater than mg. This means the normal force is greater than the actual weight. In case number 2, if the elevator is going down, let's go here. Now, sum of all forces equal to ma y. In other words, now the one or the force with the acceleration start with it. So mg minus normal equal to ma y, or in other words, the normal force, it's equal to the weight or the actual weight minus ma y, or normal force is less than the actual weight of the object. By using the given numbers in this example here, for the first case, the normal force equal to 354 Newton, which is greater than the actual weight, which is almost 300 Newton. For the second case here, the normal force equal to 234, which actually less than 300, the actual weight of the object. In all cases we discussed so far, we ignored the frictional forces. But in reality, frictional forces is very important in real life situations. Friction, let's start with the frictions. Frictional force. Now frictional forces, small f here, two types here: static friction, kinetic friction. In static friction, its Fs is defined as less than or equal to mu s n, and in kinetic frictions, Fk, it's equal to mu k n. Now let's start with static friction, Fs. Static friction is existed as long as the object is not moving, until we feel that the object is about to move. Then the static friction converted into kinetic friction. Let's have this model. In this model, as we can see here, an object with weight 14.7 Newton, and the driving force is 0, which means the object is not moving at all. So the surface here is rough. Increasing the driving force here, the object is not moving because of the static friction. In this case here, Fs it's less than mu s n. Now keep increasing the driving force until it reaches almost 3. In this case here, Fs is equal to mu s n, which means this is the maximum static friction we can reach. After that, this static frictions converted into kinetic frictions, and the object start to moving. Let's see here. The object here start to move. So the static friction converted into kinetic friction, as in this case here. In the second case here, the weight for the second object is greater, so the mass actually it's different. We start keep increasing the driving force until we break the barrier. The barrier is to break the static friction and change it into a kinetic friction. We still keep increasing the driving force until it reaches 9, almost 9 here. After that, it turns into kinetic friction, as we can see here. So Fs, it's less than or equal to mu s. By the way, mu s here is the coefficient of static friction, and n here is the normal force. This is the normal force, and this is the coefficient of static friction. Remember, Fs here it's greater or equal to 0, less or equal to Fs max. And remember, if F equal to Fs max, this means that the object is about to move. About to move. And in this case here, the net force on the object is 0. So sum of all forces on this case, in this case here, equal to 0. Once F becomes greater than Fs max, then in this case the object is moving and the friction force is called kinetic friction. So in this case the object start moving, and the friction is kinetic friction, which equal to mu k, and this is F k. In this model we have two cases. The case number 1, which is this one here, there is no driving force, which means the car here remains constant. The only forces acting on this object is the weight and is the normal force. So we have here weight and normal force. Once we give the car here a driving force equal to frictional force, in this case here the car will move with constant velocity. Let's see what's here. So as we can see here, the object is moving with constant velocity. Example: a 30 Newton block is resting on a flat horizontal surface. If a horizontal force of 10 newtons is applied to the block and the block remains at rest, what is the frictional force? Another case, the block starts to slide when a force of 20 newtons is applied. What is the coefficient of static friction? Let us consider the first case. So we have here a block resting on a flat surface. So we have here F directed this way here, and static friction in this case here. Here's the weight directed downwards and the normal force. In this case here, sum of all forces equal to, since it's resting, it's equal to 0, which means in this case F minus Fs equal to 0. In this case, F equal to Fs, or it's equal to 10 newtons. As of the second case, the block starts to slide when a force of 20 newton is applied. In this case here, F equal to Fs max, or equal to mu s n. Remember, Fs here, it's less than or equal to mu s n. So we consider the equality because it says that it's about to move. So the maximum force applied is 20, and the object after that will start moving. So it's the Fs in this case, it's equal to mu s n, or you can say that here from the y equation, sum of all forces on y, on this one here, and in this case it's equal to mg, or us equal to F divided by n, or 20 divided by 30. And remember, it's dimensionless or unitless for the coefficient of static or kinetic friction. Let's consider this case here. The coefficient of static friction, us equal to 0.75 between the surface and the block. Find the angle theta at which the object will start to move. So we need to find the critical angle in such a way the object will start to move. In this case here, let's have free body diagram. Now the weight is directed downward here. It's mg, and since theta here, so this is mg, this one here, mg cosine theta, and this one here, it's mg sine theta. Since we have frictional force, it will be somewhere like this. So this Fs. Now it should be Fs max. Why it's max? Because we are looking for the maximum angle, and after that maximum angle, or the critical angle, after that one here, the object will start to move. Sum of all forces, it's equal to mg sine theta minus Fs max. It's equal to, it's not moving, it's about to move, so it's equal to 0. So Fs here max equal to mg sine theta, and still theta is missing here. Now on the y-axis, we have here normal. It's very important here. Now on the y-axis, normal minus mg cosine theta equal to 0. and the normal in this case here equal to mg cosine theta. Now fs here max equal to, it's not less, it's equal because we are looking for maximum, equal to mu s times the normal mg cosine theta, or mu s here equal to fs equal to mg sine theta, and mg sine theta divided by mg cosine theta. Mg cancel out, so it's equal to tan theta. Since mu s here equal to 0.75, then tan theta equal to 0.75, or theta it's equal to tan inverse 0.75, or theta equal to 37 degree, and this is the critical angle. After that angle the object will start to move. Let's have another example. If an object with mass 4 kilograms and the net force acting on this object is 24 newtons, if the coefficient of kinetic friction equal to 0.2, find the acceleration of the object. To solve this, let's have a free body diagram. So let's have here, we have F here, this is F, and this kinetic friction, and we have the weight, it's directed downward, and the normal force is this one here. Now sum of all forces on X equal to MAX, in this case here F minus FK, F minus FK equal to MAX. So this equation number 1 here. Now on Y, sum of all forces on Y equal to 0, since the object has no acceleration on Y. In this case here, the normal force equal to mg. And from this, we can calculate Fk, it's equal to mu k n, or Fk, it's equal to mu k mg. You substitute this back in this equation here, you will get F minus mu k mg equal to max. You simplify this equation, you will get ax equal to F minus mu k mg divided by m, or ax in this case it's equal to 24 minus 0.2 multiplied by 40, which is 4 times 10, divided by 4, or it's equal to 4 meter per second square. Another example. In the figure shown, find the coefficient of kinetic friction between the object and the surface if m equal to 4 kilograms and the driving force is 20 newtons. Theta is equal to 53 and the object is moving at constant speed. To solve this, let's have the free body diagram. Now, let's identify the forces acting on this object. We have the weight, it's directed downward here, mg, and the normal force, this one here, and we have here the kinetic friction force. Now, to deal with this situation, we have to analyze F into X and Y components. So the X component here, it's F cosine theta, and the Y component in this case here, it's F sine theta. Now sum of all forces on X equal to MAX, or in other words, F cosine theta minus Fk equal to 0. Why it's 0? Because it's constant speed, no acceleration whatsoever. And on the y-axis here, so sum of all forces on y equal to 0, and in this case here, normal plus F sine theta minus mg equal to 0, and in this case here, the normal force, it's equal to mg minus F sine theta. Now you substitute this normal in the Fk in this equation here, you will get F cosine theta minus mu k times mg minus F sine theta. Or we can say that mu k, it's equal to F cosine theta divided by mg minus F sine theta. You substitute numbers back in this equation here, you will get mu s equal to 0.5. Again, it's dimensionless. Example: an object is sliding down an inclined surface with 45 degree. So this is 45 degree. If the coefficient of kinetic friction is 0.6, find the acceleration of the object. Now to solve this one here, let's have the free body diagram and let's identify the forces acting on this object. So we have here the weight is directed downward here, it's mg, and we have the normal force, it's directed this way here, it's the normal force, and we have here Fk is the kinetic friction. Now again, we rotate the coordinates, the xy, in such a way we match and with the y-axis. So this is x here. Now analyze the weight in this one here. So it will be mg cosine theta, and this one here, it's mg sine theta. Now sum of all forces on x, by the way, this is x, equal to max or mg sine theta. Remember, the force with the acceleration, you start with it, minus Fk equal to max. This is the first equation here. And the second equation, we have sum of all forces on y equal to 0, or the normal minus mg cosine theta equal to 0. So the normal force equal to mg cosine theta. You substitute this normal force back in this one here, you will get mg sine theta minus Fk, it's actually mu kn, so mu k, and mn in this case, it's mg cosine theta, it's equal to max. You summarize, you simplify this equation, you will get g sine theta minus mu k g cosine theta, it's equal to ax. By substituting the numbers in this equation here, you will get ax equal to 2.8 meter per second square. One last example. In the figure, if the coefficient of kinetic friction is 0.2, find the tension in the rope F M1 equal to M2, which equal to 5 kilogram, assuming that the poly is frictionless and the rope is massless. As we can see here, we have two masses, M1 and M2, and they are connected by a rope here, massless rope, and coefficient of kinetic friction equal to 0.2. The whole system here is moving in this direction. Now, before starting with this equation, we have to draw the free body diagram. We should identify the forces acting on M1 and the forces acting on M2. So starting from M1 here, the forces acting on M1 is its weight here, mg, and there's a normal force, this one here. There's a tension, let's just change the color. So we have here the weight, the normal force, and the tension. And since the surface is rough, in this case we have again Fk. Now on system 2 we have the weight M2g, by the way this is M1g, and we have tension. In this case here, sum of all forces, let's say system 1, sum of all forces on system 1 here on the x-axis here, it's equal to M1a, or in other words, its tension minus Fk equal to M1a. Now on system 2 here we have sum of all forces on y equal to M2a, or we can say that the force with the acceleration, you start with it. So M2g minus tension, it's equal to M2a. And this is equation number 2, and this is equation number 1. You add both equations together. Here you will get M2g minus Fk equal to M1 plus M2a. Now let's have the sum of all forces on y, on this case here, from the y forces we will get the normal force, it's equal to M1g. So in this case here, M2g minus mu k times the normal force, it's M1g, equal to M1 plus M2a, or a in this case it's equal to M2g minus mu k M1g divided by the sum of M1 plus M2. When we substitute this acceleration, this one here, when you substitute this acceleration in the one of the equations, it's either 1 or 2, doesn't matter actually, you will get the tension. So the tension in this case here, using equation number 2, it's equal to tension equal to M2g minus M2 times this acceleration, this guy here, M2g minus mu k M1g divided by M1 plus M2. You just substitute the given information from the question here, you will get the tension equal to 29.4 Newton. That's it for today, and thank you for watching.